is just late, they can just join us and catch the recording. Okay, so good morning. So far, I just have Rahiman and Yasmin. You all right, Rahiman? Are you fine, Yasmin?
Yes.
Okay, so let's just get started. The session is already started to record, so we have 1 hour. I just like to highlight the fact that I already went through structure and bonding last week, so this will be actually pretty short in terms of these recap of the structure and bonding, in terms of just the ideal gas equations and the origin of the ideal gas. As usual, as per the syllabus, these are how you revise and recap through the lesson objective of any A-level or any Cambridge curriculum, to be honest. So the first one we're going to do will be the origin of the pressure in the gas. So obviously we know pressure is equal to force over area from your physics. So these are the particles. The particles will collide on the wall. So when they hit the wall of the container, which you hold the gaseous particles in, or whatever particles you hold them in, as they collide with the wall, they exert a force over that area, and therefore there is the origin of pressure there. So understand that ideal gases have zero particle volume. This is just one of the many assumptions of ideal gases, and then no intermolecular forces of attraction. So far, these are the two most important assumptions. There are some other assumptions. You would have learned them in school. Some of them, they are usually three or four assumptions altogether. The usual I remember is negligible. Negligible means almost nothing at all. No intermolecular forces of attraction for an ideal gas because they are very far apart. There is almost nothing that attracts them in between the molecules. They also assume to have zero particle volume. Some other assumption includes elastic collisions. So these are other assumptions. Elastic collision means no loss of energy when they bump into each other. So it's 100% conservation of energy. What else? State and use the ideal gas equation, PV equal to nRT in calculations, including the determination of MR. In these equations, a lot of students are very unaware of what the equation actually says. This is for gases only. So it doesn't work for solid, it doesn't work for liquids, it only work for gases. This P refers to pressure of the gas. Can you tell me, Rahiman, what is the unit of the pressure of gas in this equation?
Pascal.
It has to be Pascal. Can you tell me, Isa, what is the other equivalent of Pascal? So Pascal is also the same as something else. What can you tell me, Isa?
Newton meter.
Newton meter is wrong. It's Newton per meter square because pressure is force over area. So force has the unit of newtons. Area has the unit of meter square in the standard form. So Newton meter is force times distance. That is work done. That is energy. So Newton meter, Newton and meter will give you energy, which is joule. Okay, so be very careful about your physics there. Yeah? So the V there is the volume. That is wrong, is volume of the gas. So be very careful there. And the unit there must be meter cube. The N there is mass over mR for the gas, where N is the mole. So this is the mass in gram. And the unit of mR from your periodic table, it means what is the mass for 1 mole of the substance. What is the mass for 1 mole of the substance? So 1 mole of this substance will have this particular mass. Then R is your molar gas constant of 8.31 joule per Kelvin per mole. You learn about heat capacity of solution. This is the equivalent of heat capacity for gas. When you heat up 1 mole of any gas and increase the temperature of 1 mole of a gas by 1 Kelvin, this is how much energy is required to raise the temperature for 1 mole of any gas by 1 Kelvin. This is a temperature change, so it could be joule per degree Celsius per mole. It's the same thing there. The temperature there must be in Kelvin, such that your temperature in Kelvin is your temperature in degrees Celsius, and you have to add it with 273. If you are in degrees Celsius, you add 273 to turn it into Kelvin. Of course, then you should be able to rearrange your equations, and you will be able to get like PV equal to mass over mR times RT. You want to make mR the subject. So move the mR up there. So it becomes PV times mR, mRT. So I'm doing this step by step, but in reality, as an A-level student, you should be able to do the math pretty quickly as well. MRT divided by PV, just like that. Rearrange the equation. Do not put your numbers in first because you'll be doing double the job. Rearrange the equation, find out what you want, and then put in all the values that you need after you have already identified the correct units. I won't go through the bonding again. That was basically what I have gone through in the last in the last week's class already. But just want to raise your attention to things like simple molecular. So you've got iodine, which is I2. This Buckminster fluorine, C60, as well as ice. You know, ice is this hydrogen bonded solid. So it's a very special type of arrangement. You got hydrogen bonds in between the H2O molecule throughout. The C60 looks like a football. They call it the buckyball kind of thing, but it's simple molecular. So what you have is that you have one big C60 and then another big C60. So in between the molecules, you have van der Waals forces because these are just atoms. These are just atoms which are all carbons. There is no polarity. It is non-polar. When you have non-polar molecule and non-polar molecule, all you have in between the molecule is just your weak van der Waals forces of interaction. Okay, now the same thing with iodine, but iodine is a simpler looking molecule. So simple molecule like that, where you have covalent bonds, but then you also have the weak van der Waals forces of attraction, intermolecular forces, two types of bonding there. Intermolecular force between the molecule, interatomic force between the atom, covalent bonds. Remember that when you melt or when you boil simple molecules, you never break the covalent bonds. You only break the weak van der Waals forces of interaction. And all these structure and bonding are important. What do you break for melting? What do you break for boiling? Conductivity, whether you can conduct electricity or not. Well, if you talk about ionic structure, ionic compound, we talk about free ions. We don't talk about electrons because the ions don't have free electrons. The electrons already been transferred from the metal to the non-metal. There are no free electrons lying around. If we talk about metal, okay, giant metallic lattice structure, we don't talk about anion because there are no anion in metal. It's element. All metals are elements. You think about your giant metallic lattice structure, we talk about free delocalized valence electron. When you label your diagram, you would know. If you know what the structure looks like, is to deal with free electrons there. In terms of solubility, solubility could be solubility in water. You could get ionic compounds where you can form ion dipole bonds. This is related to the concept of hydration, enthalpy of hydration of ion, which, if I'm not mistaken, it is it's no longer in AS, but it is actually part of your A2 energetics. I'm pretty sure it's in the A2 syllabus where you learn about the ion. They can be surrounded by the appropriate delta plus or the delta minus in water. It's called hydration. When you have simple molecule, they can dissolve in water if you can form hydrogen bond with water. This is for simple molecules that can form hydrogen bond with water, like your amines, like your carboxylic acid, like your ammonia, like your alcohols. This is for ionic compounds. When they dissolve in water, they get hydrated. Now we're going to be looking at a couple of questions. So I guess you already have access to these questions. I already provided a week before, so it is now open to you to raise up any questions you want me to go through in this paper. Of course, the sooner we finish this paper, I'll probably move on to enthalpy changes because there are only a couple of more weeks before your AS exam. So we won't have time to go through every single topic if we just spend one week on one topic. So, if you're happy with this, I can move on to energetics, which is enthalpy change. But yeah, I mean, let's just finish this one first. Okay, so you can unmute yourself and just tell me which question you want me to go through, which one you don't understand or whatnot. So I'm going to stop talking. Anyone? Questions?
Question 4.
Question 4. So question 4, okay. So in these questions, the temperature is that, but it seems like at the temperature changes. The temperature changes, but it's the same volume. So volume doesn't change. but the pressure change. So we know PV equal to nRT. So what is not changing? The volume is constant, the R is constant, the same mass, so the mole is constant. So P is directly proportional to T. So this is constant, and this is constant. So pressure become directly proportional to T, because as T increases, P increases, since these three are constant. So what do we have? Initially we have pressure P, but now our pressure is 2P. Now the most common mistake is people just multiply 27 degrees Celsius by 2 and they will make the mistake of 54, but this cannot be the answer because this temperature in the ideal gas equation is in Kelvin. So what we can say is at pressure P, the temperature is 27 plus 273, which will give you, what is this? 273 plus 27, this gives me 300 Kelvin. So what happened with 300 Kelvin then is at 2P, double the pressure, double the temperature in Kelvin. So 300 Kelvin times 2 is 600 Kelvin there. So the answer there must be 600 Kelvin. Okay, makes sense? I mean, it's all based on the units in the ideal gas equation. All right, any next question? Anyone else got questions? You don't come with the question on the day. You have been given the paper a week in advance. So, you know. Any other questions? No one else have any questions? Well, I guess at this point, perhaps we can all just turn our video on so that we can take a quick photo for attendance and yeah, be done with that. Okay, so I'm going to stop sharing for a while. Let's just turn on our video and just take a quick photo for attendance. Provided people are there. Okay. Hello, good morning, everyone. The AS level exam is coming, yeah? Okay, so let's smile on camera. Okay, 1, 2, 3. And we'll take another one. 1, 2, 3. All right, so feel free to turn off your camera. I hope you stay with me, and yeah, we'll continue and deal with more chemistry, obviously. That's what I'm here for. Remember, 1 hour a week is not going to be enough to, you know, for you to be very good at what you're supposed to be able to do. So try and go through more on your own, yeah, not just rely on these sessions. Okay, so any other questions in this paper on states of matter, ideal gas equations? Doesn't have to be MCQ, it can be structured question as well. It's like I don't really want to choose a question for you because, you know, it has to come from you. What do you want to know? What is it that you feel you don't know how to do? And therefore I can show you, I can explain to you how to do things. Any other questions at all? Come on, don't be shy, just unmute yourself. Question 12, okay. Sorry, I heard 2 voices just now, but it's okay. The other person will get the opportunity in a little bit, okay. These numbers are a little bit small, but what I do then is I just look at the mole of N2 here. This is given in mole, the unit is fine. This volume is in dm cube, this is not fine. The volume in the ideal gas equation, the volume is in meter cube. So I will teach you how to convert dm cube to meter cube. Now, another thing is converting cm to meter cube. A lot of students, they just memorize the conversion factor. It's actually quite a bad strategy because, you know, how much thing can your brain remember? Even I cannot remember a lot of things, okay? Now, we know 1 dm is 10 cm. Decimeter, deci means 10, okay? Deci means 10. And this is cm. What we want is dm. Actually, what we want is meter. So 10 cm convert to meter is 10 over 100. So that is 10 to the power of -1 meter because I divided by 100. So then now I get dm is to meter. This is what you do in mathematics and physics, cube both sides. Because it's equal, whatever you do on the left, you do it on the right as well. Whatever you do on the left, you do on the right as well. Now look what happened. 1 cube is 1, dm cube is dm cube, 10 to the -1 cube is -3, meter cube is meter cube. I get my conversion factor without memorizing. I just work it out from the normal physics. Now I have 3 dm cube. So this must be 3 times 10 to the -3 meter cube. So I got my thing correct there in meter cube already. Now my temperature is in degrees Celsius. So 273 degrees Celsius plus another 273 to convert it to Kelvin. So there will be 273 plus 273. There is 546 Kelvin. In terms of PV equal to nRT, I want the pressure. So P equal to nRT over V. Yeah, you know, when you're faced with this kind of question exam, do not hesitate to circle, underline, and show your working, because it is how you can understand and how you can follow your own work later on. The mole is 1.6 times 10 to the minus 3 times 8.31 times 546 Kelvin divided by the volume, which I got on the far right, 3 times 10 to the minus 3. So I can see 3 times 10 to the minus 3, 3 times 10 to the minus 3. I can see the 273 plus 273. This is still 273 that is wrong. This is the only correct answer there. Okay. Now I'm also going to show you something. This was dm cube to meter cube. Okay, dm cube to meter cube. Now let's try the same thing with cm cube. So I want to change cm cube to meter cube. So the first thing I do is I think about my conversion. This is your primary school mathematics actually. So 1 cm convert to meter is 1 over 100 meter. You divide the cm by 100 to convert it to meter. So what I can do is 1 cm is 10 to the power minus 2 meter. I want cube. So what I do in terms of physics, in terms of math is cube both sides. So what happens when I cube both sides? So this is going things a bit slow, but once you know the conversion idea very well, you should be able to do the math very well. And guess what? Cm cube to meter cube, I get this conversion factor. I never memorize this number. I know from my normal math, I can get it any day, anytime, and I will never be tricked by a simple question like this. Is it 10 to the minus 6 or is it 10 to the minus 3? When do you get tricked? When you don't know how to do things, okay? So hopefully that helps. So I heard 2 voices just now. One person asked this question. Was there another question the other person asked just now? Hello, what was the other question that people wanted to ask? Come on, just unmute yourself and just shut out, okay? I am not sure whether the connection is smooth or not, yeah, because something is wrong with the internet connections all over the country. I heard about the internet outage in Tutong and KB area, so well, I hope the session is recorded anyway, so hopefully it will help you later on. Not too sure how laggy it is on your side, but do shout out. Any other question you want me to go through?
15.
15, okay. So blah, 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 blah. The idea is most volatile. Now, volatile is an English word, okay? If I describe someone is very volatile, the husband is very volatile. The husband gets angry easily. Angry is like when you reach your boiling point. So volatile means low boiling point, boil easily. Someone get angry easily. So the most volatile mean the easiest to boil. The easiest to boil mean lowest boiling point. So lowest boiling point, you're looking for something with the lowest boiling point. These are all simple covalent molecule. When you think about simple covalent molecule or simple molecular or simple covalent structure, you are just breaking the weak intermolecular forces. Now we know that there are different intermolecular forces. There's the van der Waals, which is weaker than permanent dipole, which is weaker than your hydrogen bond. So if you want the lowest boiling point, choose the one that does not have hydrogen bond. You don't want the hydrogen bond. You want the one that has no hydrogen bond. So NH2 there can form hydrogen bond. Hydrogen bonded to nitrogen, oxygen or fluorine, and these are the delta negative, highly electronegative atom, and it has a long pair on it. Conditions for forming hydrogen bonds. So can form hydrogen bond there, C and D are out. Now between A and B, how do I decide? This is CHO. This is actually aldehyde. 1, 2, 3, 4, 5, 6 carbon. So I have just drawn skeletal formula. This is a aldehyde CH. I don't show the hydrogen bonded to the carbons. All of you should be very good at drawing skeletal formula if you want to survive organic chemistry. Yeah? 1, 2, 3, 4, 5, 6. So there is no self-respecting chemist who would not be able to draw a skeletal formula, because the moment you start drawing display formula for your MCQ, you die because, you know, how much time do you have? Skeletal formula is the most elegant and is the way to go if you want to survive, okay? Carbon form 4 bonds, 1, 2. So there is 2 hydrogen there. There's a CH2. Carbon form 4 bonds. You only show the 1 bonded to carbon. So there must be 2 hydrogen there. Carbon form 4 bonds. 1, 2 is shown there. So there must be CH2 there. Carbon form 4 bonds. So here there's only 1 bond shown. So there must be 3 hydrogen there. CH3, CH2, 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 CHO. This is called an aldehyde. That is the functional group, the name of which there are 6 carbons. So aldehyde has an Al at the end. It's something methanol, ethanol, propanol, etc., etc. This is called hexanol because there's 6 carbons and it's a 6 carbon aldehyde there. Now we know aldehydes just like your carbonyl chemistry, delta minus, delta plus. That's why your nucleophile can attack this carbonyl. And we know that aldehyde and ketone chemistry, nucleophilic addition mechanism that is in your AS chemistry. So we know this one has a permanent dipole. I mean, look at the delta plus and delta minus, which I have just drawn. Permanent dipole is stronger intermolecular force than van der Waals. Therefore, it would take a little bit more energy to break this stronger intermolecular force than just this one, which is just van der Waals. There is no permanent dipole at all. This is hydrocarbons. The hydrocarbons are considered as non-polar, even though the carbon and hydrogen, they have different electronegativity, but that difference is very, very small. Think about all your hydrocarbons. Think about your petroleum product. Petroleum products do not dissolve in water because non-polar do not associate with polar water molecule. Hopefully that makes sense there. Next question. Any other questions in the MCQ?
16.
16. So this is pretty much the same question as the previous one. Previous one was, I give you formula. Here, I also give you formula, but I also give you MR. So this is to try and confuse you. In an O-level setting, O-level, GCSE, IGCSE level, people would think, oh yeah, just look at MR. But in A-level, you know that there are different types of intermolecular forces. We don't just look at the MR. We look at the ability, whether you can form hydrogen bond, whether you can form hydrogen permanent dipoles, or just van der Waals forces. Well, let's identify this one. This is an amine. It's called an amine. And this is called propyl amine because there are 3 carbons. If I draw the skeletal formula, because I love skeletal formula, you don't like it because you don't know it. But once you learn about its elegance and how fast you can get when you do organic chemistry in AS and A2, you have to learn how, okay? You have a lone pair on the nitrogen there. So if I show 2 molecules of it, I can show hydrogen bonds between another molecule of these. So when you want to show hydrogen bond, you have to show the dipoles. You have to show the lone pair on the electronegative element. So I've shown the dipoles, I've shown the lone pair, and the very last thing I need to do is from the lone pair between the delta minus and the delta plus, and then I label hydrogen bond is between the molecule. Hydrogen bond, we get it when hydrogen is bonded to very electronegative element, fluorine, oxygen, and nitrogen, such that your bond is very polar, and you must have a lone pair on the electronegative atom, can form hydrogen bond. If I'm doing these questions, I will be thinking about hydrogen bond, permanent dipole, van der Waals. Yes, yes, and yes. Well, hydrogen bond is a special type of dipole. If you have hydrogen bond, you definitely have a polar bond there, okay? OH again, just like the previous case, which I explained, yes for hydrogen bond, yes for van der Waals, and therefore yes for permanent dipole. You have alcohol there, so that is alcohol. That is in fact alcohol as well. By right, it should really be written as HO, CH2, CH2, OH. That is your ethane 1,2 diol. Ethane 1,2 diol, and you get that by oxidizing an alkene. This is a diol because there is 2 OH at position 1 and 2 there. So definitely for hydrogen bonds, and this thing is just a halogenol alkene. So this is a good revision for your organic chemistry, which I haven't gotten to yet. 1 and 2. Carbon form 4 bond, 1 and 2. So there is 2 hydrogen there. It's called CH2. Carbon form 4 bond, 1 is shown. So there's 3 hydrogen there. This is called chloroethane. Halogenol alkane is the name of the functional group. The functional group is called halogenalkane. So you name the alkane at the end and you put the halogen in front, chloro-bromo-iodine. This is chloroethane. Now it has a permanent dipole because it's delta minus and delta plus. And you know the chemistry of halogenalkane follows nucleophilic substitution. So when you have a nucleophile like hydroxide, aqueous hydroxide, it can come in and it can attack that. You have shown dipoles, you have shown lone pairs on the nucleophile, at rich attack the poor, and then heterolytic fission break the carbon-chlorine bond there. Okay, so no hydrogen bonds because you do not have a hydrogen. Well, you do not have a hydrogen bonded to fluorine, oxygen, or nitrogen. You don't even have those fluorine, oxygen, nitrogen here. No hydrogen bond. No hydrogen bond would mean that this one would have much weaker intermolecular forces compared to something that has hydrogen bond. You don't require as much energy to break, and that is why it has lower boiling point compared with the rest of these. Okay, so D must be the answer there. Hopefully that makes sense. It's all about comparing the melting point and boiling point in terms of the strength of the intermolecular forces. Okay, all right. Next question. Any other questions in the multiple choice? You can ask me in the structure question as well. People are very quiet this morning. Come on, we're half hour into the 1 hour sessions. Anything in this topic? Anything else you want to ask?
Question 6.
Question 6. So as I said again, yeah. So this type of scenario, they're much better if you have done something. Okay. So this is a scenario. So a lot of the times, okay, it's like Spider-Man. How in the world does Spider-Man walk on the wall? Okay, it's because there must be attraction between Spider-Man and the wall. It's the same thing with lizards. Okay, obviously Spider-Man is not real, okay, superhero, but lizard can walk on the wall. That is real. You have seen it. Now we know that this bond, as they move, they do not have to break very strong bond because they can walk along the wall very easily. Okay, so we know that this attraction is actually very weak attraction. It cannot be very strong attraction. It has to be temporary. It has to be like induced dipole. And induced dipole has another name. Induced dipole is not permanent dipole, it's temporary dipole, it's just van der Waals forces. If you form covalent bond, there's like sticking the gecko onto the wall and it's not going to move at all. Same thing with this coordinate bond, which is a covalent bond. Same thing with ionic bond. These three are very strong bond. These are very weak intermolecular forces there. Okay, next question. Any other questions? Don't have to wait for your turn. You can, keep on shooting me questions. That's what I'm here for, 1 hour. Hope people are still there. Anything you want to ask? You only have me for 1 hour. No? No questions? Do you want me to go through structure question instead? If you had a look at the structure questions? Okay, have you had a look at the structure question at all? So about structure and bonding, right? Do you want me to go through them or you have a specific question you want to ask?
Question 2.
Question 2? Question 2 is about kinetic particle theory as well as ideal gas. So the kinetic particle theory is also the first topic in your O level. It's what happens to the particle. This is a very important concept. What happens to the particles? Do not talk about the things you can see. We think about the things we cannot see. State the 2 basic assumptions. You saw it in the syllabus just now. So usually question will ask you only 2. There is very rare that they will ask you list all 5 assumptions. Usually they just ask for 2, and your syllabus just now said about no or negligible intermolecular forces between the molecule. So, all of you should be able to understand that when you have ideal gas, you have very minimal intermolecular forces of attraction. If you have hydrogen bonds, that is probably the strongest intermolecular force compared to permanent dipole, compared to van der Waals. And therefore, if you have hydrogen bond, you are the least ideal because your intermolecular force is the strongest compared to just van der Waals. So no intermolecular forces of attraction between the molecules, between the particles. And the other one was 0 particle volume. that was stated in the syllabus just now, right? Of course, you can have some other one like elastic, perfectly elastic collisions, negligible volume or zero particle volume stated in the syllabus just now. Now, in terms of the conditions for an ideal gas, we always think about, well, at least for me, I always think about the most important assumptions. To have negligible or no intermolecular forces. Do you want your particles to be far away, or do you want them to be as close to each other as possible? So that's the question. Do you want them to be as far away from each other, or do you want them to be close to each other? What do you think, Yasmin? Are you with me, Yasmin? Do you want your particles to be close to each other, or do you want them to be far away from each other if you want to have negligible or no intermolecular forces here?
No intermolecular forces.
No. You don't understand the question. No intermolecular force means negligible intermolecular force. Minimal, yeah, minimal. It means minimal. So the question is, do you want your particles to be far away from each other or close to each other for this to happen?
Far away.
Far away from each other. Okay, now you want your particles to be far away from each other. Here is where it gets interesting. Your answer comes down to these two conditions. So if you want your particles to be far away from each other, do you want your pressure to be high or low? What do you think, Yasmin? So you want your particles to be far away from each other. Do you want high pressure or low pressure? Because Yasmin connection is not very strong. What do you think, Afif? Are you with me?
High pressure.
Okay, so Yasmin just answered me high pressure. So as I squeeze my pistons.
Oh, if high pressure,
yeah,
it will be.
Yeah.
The particle will be closer together.
Yeah, of course, because this one is high pressure, this one is low pressure. So you're contradicting your own words. You want your particles to be far away. When you want them to be far away, you want them to have low pressure. Okay. Now the other thing is to do with temperature. Do you want high temperature or low temperature? Since you are here with me, Yasmin, for your particles to be far away.
Low temperature.
Low temperature. Okay. Now this is your year 9. Yeah. Even I teach this in year 9. This is a heating curve. You must have seen this before, right? You know what this curve means, right? So this is the melting point, this is the boiling point, this is temperature, and then this is time. So we are applying heat, right? We are applying heat. Apply heat. So your particles gain kinetic energy. Do you agree? Your particles absorb heat as they get heated. They absorb heat. Now this is a solid. This is solid going to liquid. This is liquid going to gas, and there's gas. This is year 9 concept. Are your particles getting closer together or getting further away? Yasmin, as you go from here to here. Are your particles getting closer together or further away? Further away. So if you want your particles to be far away, do you want high temperature or low temperature? High. So you said low temperature just now, right? That was what you said at the very beginning, right?
Oh yeah.
Okay. You cannot say something without thinking about something. That goes for all of you. The moment you start saying something without thinking about the situation, that is when you will make a silly mistake. And when you make silly mistake in AS, there's no coming back. If you don't score your AS, you won't score your A2. You must score well in AS so that the marks get carried forward and it will help to add up to your A2. That's the best message I'll usually tell my students. Okay, so state the two conditions. Low pressure. They don't ask you to explain, but the question can very easily ask you to explain as well. So it could be a 4-mark question. State and explain the two conditions. In terms of temperature, well, in terms of pressure first, as you increase the pressure, you squeeze the particle closer together. So obviously when they're closer together, the particles will have a stronger intermolecular force, therefore become less ideal. Explanation number 1. High temperature. The higher the temperature, the particles have more kinetic energy, because that's the definition of temperature and kinetic energy. Higher temperature, more kinetic energy, particles move further away from each other, and therefore lesser or negligible intermolecular force, more ideal. Now place the following gases in the order in decreasing order of ideal behavior. So the most ideal will have negligible or no intermolecular forces. So here must be the weakest intermolecular forces, and the least ideal must be the highest or the strongest intermolecular forces. Now, to do these kind of questions, realistically speaking, I always think about the three things: van der Waals, permanent dipoles, and then hydrogen bonds. Okay, so I'm gonna ask Shakira. Are you there, Shakira? Shakira with me? Probably lagginess. Okay, never mind. Iza, are you there, Iza?
Yes.
Okay, Iza, does NH3 have van der Waals? Can you tell me about the van der Waals? Does all the molecules have van der Waals between the molecule?
Yes.
It does have van der Waals because there are electrons in the system. Iza, is this polar or non-polar? NH3.
Polar.
It's polar. Can it form hydrogen bond or can it not form hydrogen bond?
Can.
Can. How about neon? Is neon polar or non-polar?
Non-polar.
In fact, it's just a noble gas atom on its own. Obviously, not going to form hydrogen bond. N2, is N2 polar or non-polar?
Non-polar.
N2 is non-polar as well. So hydrogen bond is obviously not going to be a case there because there's no hydrogen there at all. So now, this is the strongest. This is the strongest intermolecular forces. Of course, you can say it can form hydrogen bonds, and therefore it is the least ideal. The least ideal is going to be NH3. Now, NH3 is the least ideal. So between neon and N2, how do I decide between neon and N2? I'm just looking at van der Waals. The question now comes back to what are the two factors that affect van der Waals? What are the two factors that affect van der Waals? You see, this is 3 marks. So 1 mark is for the trend. 1 mark is for the order. 2 marks, the 2 marks are for the explanation. 1 mark for the van der Waals. So this one is N2 versus neon. 1 mark is for the hydrogen bond to identify NH3 can form hydrogen bond, but this thing cannot form hydrogen bond. Hydrogen bond is stronger intermolecular force than van der Waals. Therefore, it is less ideal for NH3. Between N2 and neon, there are 2 factors that affects the strength of van der Waals. I talked about it last week. The most important factor is the total number of electrons in the molecule or in the atom. Now we know between N2 and neon, N2 has 7 protons plus 7 protons. There are 14 protons, therefore 14 electrons. Neon is element number 10, so there are 10 protons, there are 10 electrons. Strictly speaking, this one is stronger van der Waals because it has greater total number of electrons. Electron counting is not your molecular mass, it's based on your proton number. Okay, if you have stronger van der Waals, this one will have less negligible intermolecular force. So this one will have the most negligible intermolecular force, will have the weakest intermolecular force. So neon is the most ideal and not the other one. So what happened then is I should just put in my order. So NH3 and then neon is the most ideal and then N2 is the second most ideal there. Okay, hopefully that makes sense. In terms of explanations, talk about these for the van der Waals, talk about the ability to form hydrogen bond between the NH3 and you should be all right there. Part D is about the kinetic particle theory, why a liquid becomes a gas. Just now, I think I asked, sorry, did someone say something, Afif?
Kalau pasal dia punya N2 punya triple bond, tidak dapat di-use to explain.
No, you know why? Because no intermolecular forces. Nitrogen, nitrogen, nitrogen triple bond. This one is covalent bond. Covalent bond is between atoms. We are talking about intermolecular forces. This is between molecule. The assumptions of ideal gas does not mention about covalent bond. It mentioned about intermolecular forces. It never mentioned covalent bond. Are you breaking the covalent bond when you boil and melt? No, you don't, because these are simple molecules. We simply talk about the intermolecular forces of attraction. Does that make sense, Afif? So straight answer to your question, no. Straight answer to your question is no, because you don't break the covalent bond at all. Now this one is about boiling point. Boiling point is to do with liquid going to gas. Just now, I think I asked Isa or I explained to, forgot it was Isa or someone else, but this thing, you apply the heat to it. So we are talking about liquid going to gas here. We are talking about these green color highlighted regions. This is very common in year 9, year 10 physics, okay, where they ask you what happened here. The temperature remained constant at the boiling point. Why does the temperature remain constant even when the temperature increases? Because what are you breaking at the boiling point? Okay, so at the boiling point, the temperature remains constant. So temperature is constant for a pure substance, but we keep on supplying heat. So where does the heat energy go to? Because we know energy is conserved. So the temperature stays constant because there is no change in kinetic energy. So the heat energy that you supplied doesn't go to kinetic energy. Instead, that energy that you supply is used to make the particles move further apart. Instead, the temperature that you supply, the heat that we are supplying, the heat supplied is used to overcome. Overcome means to break, because boiling is endothermic. Therefore, you need to overcome, you need to break the forces of attraction. I do not want to talk about intermolecular forces because the question does not mention about simple molecule. It just says liquid, it just says gas. It could be a giant ionic structure. It could be a giant metallic structure. It could be a giant covalent structure. It could be a simple molecular structure. It was never mentioned in the question. So I do not assume, because if the question doesn't specify, I do not assume. Okay, I just said the most general thing I could say, the forces of attraction between the particles. So this could be between cations and anion, it will be the strong ionic bond. If it is between the particles in metals, it will be between the cations and the delocalized valence electrons. If it is the case of simple covalent molecules, then it will be the weak intermolecular forces between the molecules like that. Okay, hopefully that makes sense there. Anyway, so there's as much as I could say there. So basically it's converted to, overcoming the potential energy. That's why the temperature doesn't change. And that is why when temperature doesn't change, there's no change in kinetic energy at all. Okay, hopefully that makes sense. And your particle, what happened to the particles? The particles will slowly move further apart because you are boiling, right? So they move slowly further apart. I guess this last point is essential because what happened to the particle? What happened to the particles? I think there was one person I forgot to take the attendance of. I think Shakira Nabila, you joined a bit late, right? Am I correct? Shakira Nabila, are you there?
Yeah, yes, sir.
Okay, no worries. Okay, I think you joined a bit late, so we took the attendance photo earlier already, but it's okay. I take note of your attendance. It's fine. Okay. And the session is recorded anyway, so you can always go back to whatever you miss. All right, any other questions in the structured paper? Any other questions at all? People can I can go back to the next question. Page how many? Because I think my structure question, the numbering is a bit messed up. Which page is that?
13.
Page 13, page 13. Okay, this page, yeah? Should I go through the whole questions? Hello, who was the one who asked this question just now? Okay, Isa. All right, okay. This one, yeah? This actually relates to the topic 9, which is to do with period 3 chemistry. Okay, but it's to do with structure and bonding. So the first thing we do is aluminium. Oxygen is not as an atom, it's oxygen molecule. Al2O3, because we know Al3 plus and O2 minus, we get Al2O3, the formula of an ionic compound, where the charges of the ions get cancelled out. So you have 3 of that O2 minus. Minus 2, minus 2, minus 2 is minus 6, cancel out plus 6 there. Whatever you do, balance your equation. Whatever equation you write, balance your equation. So I personally like to balance with fractions because I have 3 oxygen atoms. So I have oxygen molecule, I cannot change that. So 3/2, fraction in front, times the 2, I get 3 oxygen atoms. Now, I know some teachers don't really like fractions, but you have done the topic called enthalpy change of formations. You know fractions are allowed, okay? If you really don't want the fractions, you can also multiply the whole thing by 2. You get 4, you get 3, you get 2 in front there. Now, drawing diagrams were appropriate. This is actually from quite an old A-level paper, but drawing diagrams are very, very, very important. This is Al2O3. So we know it has giant ionic lattice structure. So when you have giant ionic lattice structure, what we have is Al3 plus, O2 minus, Al3 plus, O2 minus, and then we are surrounded by oppositely charged ions in an alternating cation and anion. This is what happened in reality. Repeated arrays of the ions alternating cation, anion, cation, anions in 3 dimensions. So what happened is we need to break, well, structure and bonding. Structure and bonding. So the first thing I do really is I must state the structure. Al2O3 has giant ionic lattice structure. State the structure. Simple as that. Melting and boiling. So melting or boiling, what do we need to break? Okay, so melting or boiling, Al2O3 needs to break. What are you breaking? Use the correct adjective, strong, and then state what are you breaking. I said ionic bonds because these are between cations and anions. So I identify based on the questions between the cations and the anions. Therefore, you need a lot of energy to break the strong ionic bonds. Need a lot of energy. So very high melting point and also boiling point. So essentially, the key point there really is point number 1, point number 2, as well as the diagram there. Point number 3 is not really a point; it's just restating the question, to be honest. So you don't get really a lot of marks to talk about point number 3 there. The SO3 is a simple covalent molecule. So it has a simple molecular or a simple covalent structure, depends on which one does your teacher teach you. Both are equally accepted. Simple covalent structure or simple molecular structure is the same thing. So when we melt or when we boil simple covalent molecule, based on what I told you last week, only for structures, you need to identify what are you breaking exactly here. You're breaking the weak intermolecular forces, but then we also know SO3 is this sulfur-oxygen double bond, and the sulfur uses all the electrons in the outer shell for bonding. So this thing is actually non-polar, simply because you have 0 lone pair, 3 bond pair. All the 3 atoms are the same in this trigonal planar geometry, where you have 0 lone pair. This thing is a non-polar molecule. So you do not have a polar molecule at all. You do not have permanent dipoles. Therefore, we are just breaking the weak van der Waals. Again, I use the correct adjective, weak versus strong here. So this is between SO3 molecules, because intermolecular forces of attraction is not the covalent bond. So it's literally like, between this molecule and this molecule, there is van der Waals forces of attraction, intermolecular forces of attraction, not a lot of energy required. You don't need a lot of energy to do that. Therefore, low melting point and boiling point, something that even year 9 students would be able to tell you as the properties of a simple covalent molecule there. Last but not least is to do, so this is a 7-mark comparison question, quite a lot of marks, yeah? SiO2, as you know, the silicon is bonded to 4 oxygens, as stated in the syllabus, of course. You have seen it in the components of sand when you were doing O-level chemistry. And the silicon is bonded to 4 other oxygens, and the silicon is bonded to 4 other oxygens. You must not confuse between SiO2 and CO2, which is simple covalent molecule. This is a giant covalent structure there. But they're asking us SiO2 versus P4O10. So SiO2 has giant covalent structure and bonding, right? So what are you breaking here when you melt it? So melting. So they're talking just about melting point. So I just talk about melting instead of boiling. We need breaking many strong covalent bonds. This was also what I highlighted last week. I told you about the 4 different structures, and you must be able to identify what are you breaking. You are breaking the many strong covalent bonds between the silicons and the oxygen atoms. This one requires a lot of energy, and therefore it has a very high melting and boiling point. But you are comparing when you're comparing, you cannot just say one thing but not the other thing. You will know it from biology as well as from other sort of chemistry questions, that you cannot just say one thing without talking about the other thing. So I just very quickly talk about the simple covalent structure. So when we melt P4O10, so we just need to break the weak intermolecular forces of attractions. So I don't want to say specify too much without showing you the structure, but then P4O10 is actually slightly polar. Hang on, P4O10 is polar. I think P4O10 is polar actually, but just to be safe, I just write down weak intermolecular forces of attraction between the molecules, not a lot of energy. That's why low melting point compared to this one here. Okay, hopefully that makes sense there. Not too sure who asked this question. I think it was Isa just now. Hopefully that makes sense. Identify structure, identify what you need to break. Use the correct adjective so that you're comparing strong and weak, and you're thinking in terms of the energy required to break whatever you need to break, depending on the structure there. Okay? Any other people got any other questions? Multiple choice, structure, just shout out. No other questions? People are fine? I mean, this topic links really well to the last topic. It's just the new thing are just the ideal gas questions, and of course, reinforcing the ideas of structure and bonding. Any other questions, people? Should have done this, gone through this a week in advance so that you can identify your weaknesses, yeah? So same thing will go for the next topic called energetic. Yes?
Page 16.
I think page 16 is also an ideal gas question. The whole thing from the very beginning?
Sure.
Okay, I can go through it. Okay, so when I go through questions, so I'm putting myself in the shoes of the students. So, when I read through the questions, what do I know about it? The PV equal to nRT is an ideal gas equation. As I go through these questions, I need to think about the assumptions. So there were two assumptions of ideal gas. One of the most important one is negligible intermolecular forces. And then the other one is zero particle volume. And I know a couple of other ones like perfectly elastic condition. They collide with no loss of energy or whatnot. Negligible there could also mean no intermolecular forces or very weak intermolecular forces. I know in general, hydrogen bond is stronger than permanent dipole, stronger than van der Waals in general. Okay, now I look at this graph here, PV against P. If we say PV equal to nRT, N is the number of mole of gas, R is the molar gas constant, T is temperature. So PV equal to constant is part of something you learn in physics called Boyle's law. In physics, you just do the math, you just do the calculation. In chemistry, we talk about what happened to the particles. By right, PV equal to constant should be a straight line like this because PV is a fixed value. Pressure can change, volume can change. As pressure changes, P times V doesn't change because as pressure increases, volume should decrease if the temperature is constant. That is Boyle's law, something you learn from O-level physics as well, and something you will do in A-level physics as well, I'm sure. But in chemistry, we deal with this concept, ideal gas equation. It should be a constant, but look what happened. Look what happened at low pressure. So when you have low pressure, I think earlier I asked Isa or someone else. So ideal gas equations, the gas is most ideal at low pressure compared to at high pressure. So you can see greater deviation from the constant line here. This constant line here, they become less and less ideal as they become less and less following this straight line here, because this one is the one that deviates quite far away. Actually, this deviates quite far away as well. So greater deviation from ideality. As the pressure increases, not too surprising, you increase pressure, you make the molecules closer together, you squeeze the particle closer together, therefore they will have less negligible intermolecular force, stronger intermolecular force, therefore less ideal there. So these are the more ideal one, but among these T1, T2, and T3, you can see, follow this T1, you can see this T1 here, T1 is the least ideal. T1 is the least ideal compared to T2. Compared to T2, or T3? Because you can see you expect the line to be very close to these horizontal lines, but this one is far below the horizontal line. So this is the least ideal, even at low pressure. Draw one line to show what the relationship should be for the same amount of an ideal gas. So PV equal to constant there, that is actually 1, because PV equal to constant for an ideal gas equation, therefore it should be a straight line. I don't know if my line is straight or not, but it should be perfectly horizontal. Maybe my line is not perfectly horizontal. Okay, my line is probably not the perfect horizontal, but it should be a perfect horizontal line parallel to this, yeah? So just so you know. Now, which one of these is the lowest temperature? I also talked earlier about the heating curve. So the lowest temperature, lower temperature would mean that particles would be closer together. So lower temperature, the particles are closer together. If the particles are closer together because they have lesser kinetic energy, therefore the intermolecular force is less negligible, less negligible. If the intermolecular force is less negligible, it means it is stronger. If it is stronger, then you become less ideal. The 3 temperature here, this is the least ideal one. So therefore it has to be T1, state and explain. Well, I've stated that already. In terms of explanations, at low pressure, we can see that at low pressure, T1 results in the greatest deviations. So this is the use of the English, the greatest or the most deviations from the ideality. From ideality, the ideality situation is basically PV equal to constant, and it is basically the red highlighted region here. It deviates very much from the ideality at this temperature. It must be the lowest temperature where the particles don't have much kinetic energy, and therefore they must be very close to each other, and therefore they have the least negligible intermolecular force, and therefore they are the least ideal. So you say lowest, I have to use the correct superlative kind of English word to explain my idea clearly. Well, actually, state and explain your answer to 2 with reference to intermolecular force. So here I just say it deviates the most, but here I need to talk about what I just said. What did I just say? Well, the particles must be closer together in terms of particle theory. So at lower temperature, the particles have less kinetic energy or lesser kinetic energy. And when they have lesser kinetic energy, they are closer together. They are closer together and they are within close proximity. And therefore, the intermolecular forces become less negligible, because that's what the question wants. Intermolecular forces become less negligible, and therefore they become less ideal, because ideal gases assumption means negligible or very minimal or very weak intermolecular force. The less negligible it is, the less ideal it is. Okay. The next thing is state and explain the effect of pressure. This is 2 marks. So we know that at high pressure become less ideal. I'm not going to explain it to you because I already explained it in words earlier. You need to explain it in terms of the particles getting squeezed closer together. So at higher pressure, I showed you the diagram earlier. I think it was you, Isa, that the particles, get squeezed closer together. And when they get squeezed closer together, they have stronger or less negligible intermolecular force. They become less ideal because you are breaking the assumption. And therefore, you can see they are deviating further and further away from ideality at higher and higher pressure regime. Learn to read your graph properly. This is the last thing I probably had time to go through with you in 1 minute, I guess. So the mass of flask containing A, and this is containing Y. Find the difference. So the mass of, what is this? And then with Y. Okay. I guess the mass of Y there is going to be the difference. So that minus that. We're just finishing, yeah. Blah, blah, blah. So there's 0.059 gram. You want the MR of Y. This is the density of A. That's the density of A. That is the density of A. So density is mass over volume. Do we have volume here? I don't think the density has an effect on this at all, because this is the density of A and it's not the density of Y. Okay, you want the molecular mass of Y. So everything, PV equal to nRT, is for Y. So that means the Y, just like any gas, will fill up the volume 100 cm cube. I showed you earlier, 1 cm is 10 to the minus 2 meter. So 1 cm cube is, when you cube both sides, you're going to get 10 to the minus 6 meter cube. So change that to 100 times 10 to the minus 6 meter cube there. Temperature, change that to 26 plus 273. I get 299 Kelvin. And I think Rahiman earlier told me about Pascal and Newton per meter squared. So that one is okay. So if I have all that, and I know my N is mass over mR, RT, rearrange mR, that's going to be mRT over PV. My mass is okay. My R is from data booklet. My T is 299 Kelvin. My P is pressure. My V is in meter cube. I changed the 100 cm cube to meter cube there. So hopefully that makes sense. And you can just sub everything to the calculations and you get your final answer. This is gram per mole because 1 mole of the substance has this particular mass. There's the unit of mR there. Okay, it's 9:46. I should probably let you go end this session because you have another class after this. Okay, have a good day, everyone. So make sure you go through the annotated PDF and yeah. I mean, I will upload the enthalpy change, which is the next topic that we will do next week. So please do go through that, on your own. And if you are going to submit something, submit it by Wednesday, so I have time to check. Otherwise, we'll just discuss it next Friday. Okay. Have a good day, everyone. The video should be online either later on today, this afternoon, or tomorrow after I have finished processing it. Okay. Thank you. Have a good day.
Thank you, sir.
Okay. Bye-bye.
Thank you, sir.